Good afternoon. Good afternoon. Thank you. I know it's afternoon and day 3 at Global Conference, and this is going to be a session worth waiting for. So thanks for joining us. By the way, I'm Paul Irving. I'm the chairman of the Center for the Future of Aging at the Milken Institute, and so this is a session that's of particular interest to me, and I know it will be for you too. The increases in human longevity in the past century have driven unprecedented economic growth and human potential that would have been unimaginable to our forebears. Advances in global health, in medicine and sanitation, in safety have really changed lives forever. But we stand on the precipice at the doorway of really extraordinary new invention, new innovation, and new ideas. And today we're extraordinarily fortunate to be joined by two of the pioneers in thinking about this. People who will change our lives, are changing lives today, and will change our lives tomorrow. And I want to introduce them and thank them for being with us. First, I want to introduce Craig Venter. For those of you who don't know Craig Venter, and I'm sure most of you do, Dr. Venter, J. Craig Venter, is regarded as one of the leading scientists of the 21st century. His numerous contributions to the field of genomic research are legend. I won't go through them all, but suffice to say that he has a resume that is hard for me at my age to carry with its litany of accomplishments. In addition, Craig has started with our other guest, Human Longevity, Inc., which is focused on extending the healthy, high-performance lifespan of all of us. And in addition to his role at HLI, Craig is the founder and CEO of the J. Craig Venter Institute, which is a nonprofit, both of them based in the San Diego, La Jolla area. As many of you know who are interested in genomics, in 1998, Craig founded Celera Genomics to sequence the human genome, and in February 2001, he made history by publication of the human genome in the journal Science. Craig has authored more than 280 research articles. He's a member of virtually every important scientific organization, and the honors, as I say, are a very long list. And we're very, very pleased to have Craig with us. Joining Craig, and by the way, the co-founder and vice chairman of Human Longevity, Inc., is our friend Peter Diamandis. Peter is also one of those rare human beings who sees the world and sees life in a very, very different way. Peter's the chairman and founder, as many of you know, of the X Prize Foundation, which leads the world in designing and operating large-scale global competitions to solve market challenges. Peter is the co-founder and executive chairman of Singularity University, a graduate-level Silicon Valley institution that studies exponentially growing technologies and their ability to transform industries and transform lives. Peter's also the co-founder of Planetary Resources, a company designing aircraft to enable the detection and prospecting of asteroids for fuel and precious materials. Peter has a new book out, maybe he'll mention it, a relatively new book called Abundance, The Future is Better Than You Think. And he also authored Bold, How to Go Big, Create Wealth, and Impact the World. So speaking of bold and speaking of big, these two will be talking about an issue which is as important to all of us and our families and our societies as any issue before humankind. And so please join me now in welcoming Craig Venter and Peter Diamandis.
Thank you, Paul. Hey, Craig.
Haven't talked to you for a long time, Peter.
Wow. So Paul and Mike suggested we have an intimate, confidential conversation here this afternoon.
That's a board meeting.
on a subject that I think that both of us care deeply about, which is healthy aging. I still think of myself as about 27 years old inside. I don't know about you. But to start off, let me throw out the first question, which is, this is the 20th anniversary of you sequencing the first genome. What genome was that?
So it was a bacteria Haemophilus influenza that causes ear infections in children. Your kids have probably had one or two.
And the 15th anniversary of sequencing the human genome.
Yeah.
So just to kick it off, because one of the things that is fundamentally different that gives us the sort of the traction and the tools to start thinking about understanding and affecting human aging is our ability to actually understand the human genome at a brand new level than ever before. But if you just take it back a little bit, I'd love to hear the story of what were you facing sequencing the first human genome? What did you expect to find out? And what did you actually find out?
So when I turned 95 and Peter turned 80, we started this conversation about healthy aging and felt we needed to do something about it. And you can see it's working well already. And it's something ever since my team sequenced the first human genome 15 years ago, waiting for this moment of what's changed. So 15 years ago, it cost $100 million for the first human genome. It took 9 months. We had 350 sequencing machines. We spent $50 million on a computer that today, this giant room, probably twice the size of this, with this computer now can be replaced by a card on a PC. And so when we got together with our third co-founder, Bob Harari, we decided it was now time to really start this. And the biggest finding, some of you might remember 15 years ago, was that we only had 20,000 some odd human genes. A lot of scientists and people wanted there to be 300,000 or more, so there'd be a nice linear relationship between genes and human traits. And the genetics community still tries to do this simplistic interpretation. We talk about the breast cancer gene, the colon cancer gene, the Alzheimer's gene, et cetera. And life is more complex than that. And by the nature of having fewer genes than people expected, most things are going to be combinatorial. So it's what we decided is different today than 15 years ago. Having one genome or even a few dozen or a few hundred or even 1,000 is not very useful. It was useful for the pharmaceutical industry early on to find new drug targets, but we all differ by about 3% from each other. But it's a wide, varying 3% across the genome. Most of us have very unique traits, unique to our genomes, on the order of 1 in 50 to 1 in 500,000 in the population. And so you don't find those just with small numbers. So we decided we had to do large numbers, and we had to do some unique approaches in computing. So we've we started HLI about 18 months ago now. We built the world's largest human genome sequencing center in La Jolla, and taking some really unique approaches to computing. So Peter, why don't you talk about artificial intelligence and machine learning a little bit, because you've been looking at that for a long time.
So, I mean, through the venue, I executive chairman of a university called Singularity University up in Silicon Valley, and we spent a lot of time looking at AI, what we call infinite computing, data mining, data learning. And the realization is that the companies that are really crushing it today, the companies that are the most successful, are all data-driven companies. And as we start to digitize things, we begin to be able to manipulate that at near, exponentially growing power and manipulate it for very little cost. So if you look at companies like Uber, like Google, like Facebook, they're all data companies, they're all data-driven companies. And our passion around HLI, and it's something that Vinod Khosla says, is that we're going to learn more from data sciences and life sciences than all the other biologies put together. And I believe that very fundamentally. So what's different than when you sequenced the genome back 15 years ago is that you don't have to have a gigantic, twice the size of this ballroom computation. If you had that, you have now the ability to really process and mine hundreds of thousands and millions of genomes. And I think one of the things that the sheer power of data, of large amounts of data to extract useful information is huge. And so one of the things that we did at HLI was Craig and I successfully recruited a guy named Franz Ock from Google, who was there for 10 years. And Franz ran Google Translate. And what he did was he was able to take 90 different language pairs around the world and learn how to translate them, not by understanding the meaning, but by understanding the information extractable from large data sets. And so what we think is going to be possible now through HLI, through other companies, because this is a huge industry, huge potential industry, is to really mine massive data sets of genomes and things beyond the genome to extract useful information. Understand everyone who had this set of phenotypic or medical records also had this genome sequenced, or vice versa. And so, Craig, I mean, you've been ahead of the curve here on this. What else besides the genome is important to data mine to really extract the value proposition here?
So ultimately, we will be able to tell each of you a tremendous amount about yourself and your future from your genetic code alone. But we have to go through this transition phase of discovery to get to that point. This is another anniversary. It's the 5th anniversary of us making the first synthetic life form. And we showed by writing out the complete genetic code, starting with ones and zeros in the computer, that the synthetic chromosome contained all the necessary information for life, which means that linear code contains all the information for our lives. Now, we're an adaptive species, and we adapt to our environment, but in a relatively highly DNA-programmed way. So in order to interpret this information, we're generating all kinds of capturing clinical data, we're capturing phenotype data, which includes we're measuring the microbiome. So each of you have twice as many bacterial cells as human cells. Doesn't matter how often you wash your hands, they don't go away. And they're a key part of our biology. We're measuring 2,400 chemicals in the bloodstream. 50 chemicals circulating through your brains right now are from bacterial metabolites of the food you had for lunch and of our human-made chemicals. So we're part of this complex ecosystem that we have to measure all this information. We're measuring brain MRI images, and some of our colleagues at UC San Diego came up with this phenomenal algorithm that takes a complex MRI image and converts it into the volumes very precisely of the different brain regions, which means we can compare those to the genetic code and work out what parts of our genome are responsible for these brain structures. Basically, our colleague Franz Ock is trying to set up this system where anything that we can accurately measure, we can find the genetic component of it. It turns out about half the brain, or half the genome codes for the brain. So it's not just 1 or 2 genes, it's not a chromosome. So finding this integrated information across the genome of what codes for different brain structures is going to be very exciting and very predictable in the future. We've talked about as imaging gets more precise and we get down to single neurons, we can work out the genetic basis of that neuron being where it is. With rodent studies, the same neurons show up in the exact same place in the brain of every animal, plus or minus a few microns. So we know it has to be genetically controlled. So the future might even be able to print out a map of your brain straight from your linear genetic code as we start to understand this. And we're doing an exciting clinical project in La Jolla called the FACE Project. We actually take 3D photographs of people's faces. It generates...
Before you jump to that, explain one of the questions of why we did this, because I think it's very important of the origin of this.
Well, there's several reasons. It's trying to predict everything we can predict, and it's trying to show each of us that your genome really does code for you. So we're trying to show that we can create a photograph of you from your genetic code. And so we generate these 30,000 data points, and then they're going into our machine learning system, and we're getting so we can predict a very accurate equivalent of a photograph from you right from your DNA. And the implications of this, as you can imagine, are huge, because it means you cannot de-identify the human genome sequence. People are told right now by the government that if you donate your genome sequence, they can protect your anonymity, and all these studies could be done in a completely anonymous fashion.
It also means if you're a thief, you better not leave any DNA around.
Yes. From your fingerprints on the glass, we'll be collecting the glasses after the session to expand the database. We could actually generate a photograph of you. And so it has implications for privacy. And so one of the things we spend a lot of effort on, we hired for the top guys in this field in database security. They were in the Secret Service, and they were advising the bank industry and others on data security. So we're treating everybody's data with the highest degree of security because you can't anonymize it, you can't de-identify it. But your DNA will give a picture of you. It'll give a literal picture of you, and we hope we can get it with that type of information. It can give an actual predictive picture of you as well. So because of that nature of those predictions, we think it's important to keep the data private and secure, but we think it's going to transform health. And we're not looking for the magic gene or elixir for aging. There's others working on that. We wish them success. Our view is we have to solve the human condition across the genome. We're looking at people as a whole. The primary diseases that we all die from are heart disease, cancer, and if you don't die from those at age 85, you have a 60% chance of having dementia. None of those are great outcomes. So we think right now, using your genome and the combination of MRI imaging, we can tell you whether you will develop demential symptoms 20 years before you get them, which turns the whole pharmaceutical approach to preventative medicine upside down. Instead of testing a drug on people with severe dementia, we can now in the future test it on people 20 years before there's any symptoms. It's known genetically in rodent models you can totally prevent Alzheimer's disease by changing a single gene. It's almost impossible to unwind all the damage that's done once it occurs. So preventative medicine is one of the themes we're really working on, and we feel we have to solve these things across the board. And like sanitation and other changes that allowed us to live longer than our ancestors today.
The numbers are pretty amazing, right? You can go back to Roman times. The Romans kept very good records because of probate, and the average age back in the Roman Empire was about 26 years old. Fast forward to the early 1800s, and we had improved the average age to about 28 years old, which means most of us would have been perished by then. And we've, of course, through sanitation and cardiac and even some treatments in cancer, tripled the human lifespan in that regard. But the challenge now is how do we actually expand it even further? How do we make the mantra that at least I, for one, am on is making 100 years old than you're 60. How do we do that? How do we add healthy human aging? When I was in medical school years back, I set a multi-100-year lifespan as a target. And it was a crazy idea. It was for no other basis. And I'm not proposing we're going to multi-100-year lifespans, but I'd like that. That's a good target to have. You need to be shooting for the stars. But it's the realization that there are large, complex life forms, from sea turtles to whales, that live hundreds of years. And if they can, why can't we? And that secret is in our genome. We're going to understand that. The other thing that is fundamental that people don't realize is that, as we grew up, we would become reproductive at the age of 13. We would have a child. That's when we grew up, when thousands of years ago, on the savannas of Africa.
I thought you were speaking for yourself.
No. Our great ancestors would have a baby at age 13. They would then help that child grow to reproductive age at age 13. And then they would be a burden to their tribe. They would be eating the food of their grandchild. And so the only decent thing to do back then was to die and return your parts back to the ecosystem. Add to that the fact that after a woman's reproductive age is over, and there's no evolutionary pressure to have cancer, heart disease, neurodegenerative disease, have a negative feedback cycle. So there was never any reason for the human organism to live past the age of 40. Of course, we're now going from evolution by natural selection, Darwinism, to evolution by intelligent direction, which is the use of science and technology to extend the human lifespan. And that's really the fundamental basis for what we're working on.
So what's the downside of this? You wrote about abundance and bold. We're wiping out the planet's resources as we approach 8 billion people. If we extend human lifespan to 125, we're going to have 12 billion people, and the planet can't support that. So is this irresponsible socially, what we're doing? So
first of all, I would say that I'm on a pedestal to answer just that. The quickest way to reduce population pressures on this planet, there are two of them. You make a population healthier and more literate. Bill Gates has a great TED Talk on this. If you look at, for example, the country of Morocco, 30 years ago, there were 7.8 children per family. The new king and queen came in, they put in better health systems, better educational systems, and the reproductive rate dropped to 2.8 children per family. The wealthiest cultures in the Americas and in Europe and in Japan are in negative decline. So I think that as we make the world healthier and better educated, and I think we're going to disrupt both of those. So healthcare and education are going to be massively disrupted this decade in a huge way. I think we're going to start to reduce the population pressures. And also, my whole book I wrote, I won't pimp it, but is the idea that scarcity is contextual. There's nothing truly scarce. 5,000 times more energy hitting the Earth's surface from the sun than we use as a species. We live on a water planet. Yes, California's got a water drought next to the biggest water supply in the world, the Pacific Ocean, but there's new technologies from Dean Kamen's slingshot to graphene to other material sciences that will give us water. I think it's about technology that is increasing access to these technologies. And I think the biggest economic boom we're going to see is as people who approach 65 and 70 don't retire, but are in the midpoint of their lives. They can continue for the next 20 or 30 years to be productive members of society.
Well, we've argued if you change the retirement age to 75, the Republicans lose all their entitlement issues. Water's so scarce here, we import it all from Fiji in California.
So, Craig, one of the questions is, because I know there's folks from the pharma industry and insurance industry, genome sequencing at massive scale, and we're talking about, the price right now is what, and where do you expect, it dropped from $100 million 15 years ago to what is it today?
It's right around $1,500 if you really count everything involved with the sequencing part. But
and then
it's still changing with Moore's law, and these machines that we have, the fastest ones in the world, they cost $1 million each. Each one of them is 1,350 times all of Celera. And we have 24 of these. But I announced that we hope to throw them all in the dumpster within 2.5 to 3 years, because the technology is still changing very quickly. So if 5 years from now it costs more than $200 or $300 to do a genome, something will be wrong. But it's already low enough the cost doesn't matter anymore. It's the it's the compute, it's how we deal with the information, it's the privacy issues. But this is going to totally change and has already changed in the pharmaceutical industry.
How?
Genentech and Roche was our first customer that we announced last year. It's very clear now that if you use a genetic determination of subpopulations that respond and don't respond to a drug, you can get a clinical trial approved with 100 patients in a very short period of time instead of using tens of thousands of patients and having a statistician decide whether the drug worked or not. One of the best examples I use is with lung cancer. Pfizer was doing a clinical trial on a drug to treat lung cancer, and it failed miserably. Then a retrospective analysis looking at a gene called ALK. The gene actually breaks in the middle, so it's called a translocation. Turns out 4% of lung cancer patients have this ALK translocation. If you have that, the Pfizer drug is more than 60% effective of knocking down those tumors. So that's probably the best definition you can get about precision medicine and where we're trying to have it go. So it's trying, instead of giving the same drug to everybody, in this case, 96% would get no benefit and they'd probably get harm from it. The 4% that get benefit get tremendous benefit, potentially life-saving benefit, but it's expensive. It costs $100,000 a year, but the insurance companies don't seem to have an issue with it. They'd rather pay for it where they know they get a response than paying for it to go to 96% of the people that it might actually kill sooner.
I was with one of our investors, Martine Rothblatt, yesterday. She's the CEO of United Therapeutics, and her prediction is that every drug trial in the world, well, in the United States at least, will require genome sequencing by the FDA within the decade.
Yeah. Now, we've met with the head of the FDA, and our recommendation is they require this sooner than later. It would change the cost and the time of clinical trials, and we could see potentially a tenfold increase in the rate of new drug availability for the population.
I mean, it's a sin. I mean, the fact of the matter is that the process right now and the delays are costing lives that we never measure. So that's always a challenge.
Yeah.
And insurance, how is this going to affect the insurance industry?
So it's a challenge, as you know. The life insurance industry has always been using genome information. They just don't call it that. They take your family history, they measure your blood pressure, they do an EKG, they measure your blood lipids. They measure all these things that are directly caused and determined by the genome, trying to determine how long you're going to live. The biggest risk for disease is age. It's the #1 risk factor for almost any disease. That can be changed with using this information. With our very large populations, we're trying to get at least 1 million genomes by 2020. We think we're going to be able to get very accurate predictive information.
Isn't that a low number?
It's a low number compared to almost 8 billion people in the population in terms of the amount of data. So 10 million genomes just in ACs, Gs, and Ts, 10,000 genomes gives us well over a petabyte of data. So petabyte computing has only appeared in the last decade. And so that's just the genome data. When you add in 2 gigs per MRI and all this other information, we're dealing with a massive amount of data. So 1 million genomes is more than the existing compute infrastructure can handle today. Within 5 years, it'll be a few orders of magnitude faster, so we'll be able to deal with it. So we're counting on constant changing and computing to keep up with the rate of data generation.
Yeah, I would say...
But, in the future, the compute will be able to keep up with everybody admitted to a hospital, the first thing in healthcare, the way we're trying to do it, any newborn child, the first thing that happens, perhaps even before circumcision, will be getting your genome sequenced. It's much less painful and probably more beneficial in the long run. So it will be a change in the use of information and the scale of it, but it's dependent on a scale of computing that is hard to even imagine today.
One of the things we realize is that the level of what we're trying to do right now is just become possible. And I know when Bob and Craig and I came together, it was the question of, is this the right time to do this? And Amazon Cloud bandwidth, storage capacity, processing capacity, all of that is just now making it possible to do that, and then add on that the level of machine learning to actually extract the insights. Because, I mean, one of the things that was interesting was one genome. I mean, one of the things I was shocked by was when your genome was sequenced and published, how little value it was. Not there was your genome that was little value, but a single genome was little value.
It was the same, so it's all right. Yeah, it was actually quite valuable in many respects. My mother kind of likes it, but we can't tell much more today than we could 15 years ago on my genome, because we don't have this massive data set for comparison. So it's an essential part, but the computing has been so limiting that it's, that's why we had to have such a big computer just to assemble the first genome. So this is an exciting era. The cliche is big data. I don't think most people understand what big data is going to be as we put all this complex information together to predict future outcomes. But on the insurance side, predicting future outcomes is going to be very critical. Health insurance is more complicated. I actually helped get the GINA laws passed that says employers and insurance companies can't use your genome to discriminate against you. And right now that has health insurance companies quite nervous about these issues of how do they use it for making pricing decisions, et cetera. But the health insurance industry is kind of turned upside down in this country. Most major corporations self-insure. So self-insurers are more concerned about longevity and the health of their employees than health insurance companies, where you bounce from company to company. So the other program we have is we're starting in September the first HLI clinic in La Jolla. We have requests to put these all over the globe, but we're starting in La Jolla, where you can come get your genome done, your microbiome, your MRI imaging, all your chemicals, and have us integrate this information to give you more information about you than you get from any other source. Companies that self-insure are very interested in this type of data and trying to help their employees live longer, healthier lives, because they're economically interested as well as invested in the people. So it's not clear how health insurance is going to evolve. We've discussed maybe we should start a new health insurance model based on the genome and based on the predictability of this information. The good thing with the new laws from under President Obama is the no pre-existing condition, but that's also turning the insurance industry upside down. I guarantee everybody in this room and everybody listening has pre-existing conditions when we sequence your genome. So the new rules really help with the future of insurance as we understand and can predict these outcomes. So we have to develop new economic rules around this, new social rules, and new privacy rules because of the complexity of the data. So I have a question for you. So you wrote about abundance.
Yep.
And you're such a bold predictor with your book on bold. How do you see this changing society and how quickly?
I mean, one of the questions becomes, what's the social contracts we have today that assume a 55, 60-year-old lifespan, right? Till death do you part when you get married at age 25. Is it different if you're going to live till 125? I don't know. I mean, honestly, is it?
I was asked if I wanted to live forever, and I said, after the 10,000th wife, it could get a little boring.
Government's going to have an interesting question with Social Security. The contract we have between government and individuals is going to be different. I think how we educate people is going to be completely different when you have multiple careers over your lifetime. I mean, one of our of my beliefs and precepts, and this comes from our third co-founder, Bob Hariri, who says, so the mantra is having the aesthetic, the cognition, and the mobility well into your long life, right? So looking good, having mobility, and having your cognition, I mean, because that's really what we care about, it's healthy aging. The last thing you want to do, but if you have that, you then have a chance to really to explore and live a multitude of lives. And I think that's going to be an interesting part. But I think about, I have two 4-year-old boys, and I think about the notion that they're going to have a very different life plan than we all had, where you go to school for 4 years, you get your education, and then you expect that education to last you the rest of your lives. It's such an antiquated concept, right? So it's going to be a continuous education and learning as we go forward. Anyway, that's my thoughts. I mean, one of the other big ideas, the realization is that the old adage, you can't take it with you, but I think we're going to start to, today we spend some huge amount of our net worth in the last 10 or 20 years of our lives. There's something like 60 or 70 trillion dollars locked up in people over the age of 65. And I think one of the greatest economic booms is going to be capital spent by people to extend their healthy lives. And those will be the early people who bought the expensive suitcase-sized cell phones, and then they benefited, and eventually now we have teenagers in Mumbai buying cheap cell phones. So the wealthy will pave the way for better longevity capabilities that will eventually permeate down to everybody.
So the third leg, and Peter mentioned our third co-founder, Bob Hariri, is one of the stem cell therapy experts on the planet. And so we wanted to have this component not where we could just predict your future, but we could give you something to change the outcome. So stem cell therapy is, I still believe, one of the most exciting venues for the future. So we're in the early phases of that, and we're going to do some unique clinical trials. Peter mentioned strength. So your muscle mass is more predictive of how you will age in a healthy fashion than your basic metabolic rate or almost any other factor. So you should buy some weights and at least start to work out with that. But we're going to try these placental cell lines that Bob developed at Celgene to try and treat sarcopenia, to try and increase muscle mass, because as people are stronger, their bones become less brittle, they're less likely to fall and break a hip or some of these other things that lead to all the complications in the extreme elderly. And I think as people can play more productive lives, I think it will change the health economics of the system as well. So it's early stages on that, and many of you have probably seen the recent controversy about the Chinese using this new Cas9 genome editing tool to edit a human embryo. I've taken part in an op-ed on this, and other people have written recent editorials that we should not try and edit the human genome at this stage, because our knowledge is probably less than 1% of the genome, but it is inevitable. If we can make changes by correcting errors and getting rid of disease, I think that will be an overwhelming desire of humanity to do that. We just have to make sure you're not changing other factors. Just for an example, in Drosophila, the fruit flies, depending on how you define the function of a gene, there's a protein in the wings that determines the structure of the wings in fruit flies that early on in development is a key gene for developing the proper body structure in wings. So many of our notions in modern science are pretty antiquated, that there's a single function for a gene. And so we don't want to make an edit or eliminate what we think is a disease gene and find out it was a key developmental gene. So we have a lot to learn before we do this editing, and we can obviously set the standard in the US, but what happens globally is going to be very important. And just understanding this information is important. two examples we give. One is with breast cancer. I think almost everybody's aware of the BRCA1 and BRCA2 genes that can predict risk for breast cancer. Most women that have had changes in those genes that can be associated with cancer are told that they have a 90% or better chance of getting a breast cancer. I think most people are aware of Angelina Jolie recently having a double mastectomy and having her ovaries removed because of these gene predictions. But it's not just because of those. If every woman in your family and your extended family has breast cancer, your grandmother, your mother, your aunts, your sisters, and you have these genetic changes, the predictions are very accurate and very valid. And the overall population of women without that family history, it's at best a 60% risk of getting breast cancer. So that means at least 40% of women with BRCA1 and BRCA2 gene changes don't get breast cancer, which means they have to have other genes that protect them from getting breast cancer. Because my genome was the first one done and published on the internet, it's been known for a long time that I have increased risk genetically for Alzheimer's disease. So working with experimental neurologists, I underwent a brain scan that actually measures the amyloid protein in the brain, and I assumed I would have that because of this increased genetic risk. It turns out I had absolutely none, which means I have a clean bill of health, at least for the next 20 years in terms of Alzheimer's disease.
Our investors were very happy about that.
Yes. They made me do it under a pseudonym because they were worried I would scare investors and partners. And so they asked me what name I wanted to use, and I said Charles Darwin. And they said, oh, that's too obvious. But it means that I have to have other genes in my genome that mitigate the risk by this ApoE4 allele. So part of what our goal is to give people truly accurate information, not just measuring the risk associated with one factor or one gene. And so the level of predictiveness that's going to come out of looking at complex information across the genome is going to change how we practice medicine, how each of us make decisions, and this is going to be very important. And that's why the FDA has been so concerned about some groups that only have partial information, because if you're going to make key medical decisions, such as having a double mastectomy or your ovaries removed, you want to make damn sure you have the right information and that it's really predictive. So that's one of the things that's going to change very dramatically. And obviously that gets back to changing healthcare costs, changing insurance rates, because even if you have those genetic risk factors, if you have the other genes that mitigate that risk, your overall health risk is very low, and therefore your predicted longevity will be much higher even without any kind of treatment. So I think that's part of what you're going to see in the future. In fact, I predicted recently this next decade is going to have more discoveries than the last 100 years, in part because of all the changes in computing, the changes in machine learning, artificial intelligence. So we're dependent on all these other fields, but for the first time in history, we're going to amass more information about the human species than we could even imagine 15 years ago.
Let's face it, I mean, the fact of the matter is, we do have a genome that codes for everything we do in life. It's going to code for your probabilities of coming down with cancer, probabilities of coming down with heart disease, probabilities of all these interactions, and our ability to understand that is only possible in this mass scale. This data mining, this mass correlation of all these elements that make up your book of life and your results. And understanding that is the first thing, understanding why some people live to 105 and others don't, why some people come down with cancer or heart disease or neurodegenerative disease and others don't. And that's the first step. That allows targeted drugs and treatments for you. And the flip side is, we all have coursing through our blood and our bodies stem cells. We all have this regenerative engine that is keeping us youthful. Over the course of our lives, we go from the fine softness of a child's skin, where we're making all of these collagen molecules, and then for some reasons we start to produce less of those collagen molecules. All of this is genetically programmed. Stem cells have the ability to go in and repair most oral organ systems. But the problem is that your stem cells age, they undergo insertions, deletions, epigenetic changes over the course of your life. So the question is, if we could understand all these things and start to provide you the right medicines, or eventually, if you want to predict, the return of your stem cells to their youthful self and reintroduction to your body, can we in fact rejuvenate your regenerative engine? I mean, this is what we have today at our fingertips. And it's the first time ever. It's the first time we have the ability to even ask these questions. But the value proposition is in the trillions of dollars, right? There's no greater opportunity and no more important data in the healthcare world than the data that we're talking about and other companies are talking about right now.
So we have a few minutes left. Maybe we can talk about the magic word called enhancements, when some of the genes associated with extreme sprinting ability or long-distance running were found. Several companies cropped up, and young families were paying a lot to see if they could predict what their kids would do. So it's going to be one of the challenges for this field of, it's not just about eliminating disease, as we uncover what makes the Olympic athletes great. It's a tremendous genetic screening program.
We will know at the end of this which genes correlate with what type of performance.
Yeah.
I mean, talking to some of the large sports teams out there, I mean, there's, again, huge value. This is the most valuable information, period.
But it gets into individual rights. So we think it's possibly going to be predictive whether someone has increased genetic risks for developing dementia or Parkinson's from brain trauma. So should they be allowed to play soccer or NFL football? Is it their right to do so and make this determination? Is it their risk? Is it the league owners? Whose risk is that? And how do we make these decisions? All this was captured in a movie quite a while ago called Gattaca, where it was screening people genetically for long-term space flight. By the way, we're having discussions with NASA on screening future astronauts, who should go to the moon and who would likely survive those trips. And it was a young man that had a huge genetic risk for cardiomyopathy and would likely die within 6 months of being in a long-term space flight. But he was the hero because he stole somebody else's genetic identity so he could go on this space flight. So we're going to have all kinds of new social issues that haven't cropped up at this level.
When the politician, you shake the politician's hand and you grab a couple of skin cells and you say, probability of Alzheimer's in the next 10 years on this guy is pretty high. Yeah. How's that in your political campaign?
Yeah. Well, it would have been clearly predictable that Ronald Reagan was quite far along with Alzheimer's with a simple MRI imaging test. Maybe that made him a better president. We don't know. But I think it's going to be an exciting part as we really uncover what makes us human. We will be able to understand in the next decade or two the difference between nature and nurture. And you saw with your own kids, they were very different, even though they're twins.
Yep.
Right? And so the genetic program...
I'm so dedicated, I'm doing a twin study myself.
Yeah. So it is exciting. That doesn't mean everything's genetic, but I think it's a much higher level than we ever thought before. So I'll give you last word on everything.
I think the last word in this field of fountain of youth, of aging, there are a multitude of companies working in this area. You guys have heard recently, Google's committed $1 billion to what they're doing. We have had an extraordinary set of A-round investors. 90% have come into our B round just now. There are a number of Silicon Valley's finest who are beginning to realize that the power of data is going to be more powerful in implementing biological change than ever before. So it's really the convergence of all of these technologies, the convergence of rapid genome sequencing, low-cost genome sequencing, data mining, computational power, stem cell biologies, all of these things coming together to give us the power to, for the first time ever, pursue this fountain of youth. It's not a matter of if. We will impact healthy human aging. It's only a matter of how much. Is it 20 or 30 years? Is it 50 years? My friend Ray Kurzweil talks about living long enough to live forever. And really, that's the exciting part for all of us and for our children. So,
Great.
Craig,
Thank you.
pleasure.
Thank you.
So the future of aging is very exciting, courtesy of people like our speakers. So I want to personally thank Craig and Peter for joining us, and I hope you all enjoyed this as much as I did. Thanks again.